Hello, welcome to the Express, the Express channel. My name is Roger Jones, and I'm coming to you from steaming Pensacola, Florida, out in the Panhandle. And I have not left air conditioning in 3 days. But we do have some interesting, good news here in Pensacola. Yesterday, a ferry service was started. Uh, the ferries start here in downtown Pensacola, just a few blocks from here. Uh, they go out to the beaches. They go out to the historical military sites, forts and such. And I'm quite looking forward to taking a ride. I mean, for a nerd, a ferry is about as good as a train. We're here to talk about big ideas in science, art, and society. And actually, the title of today's topic conversation is Temperature and the Speed of Thought. Now, many of you might not think temperature can be all that interesting, but it actually is. And we're going to go right to the edge of human understanding and the philosophy of what humans can know about themselves and the universe just by looking at this question. But before we go there, I need you to look at something for me. I need you to look at my T-shirt. See what it says? Serotonin. Serotonin is one of the two things that make me happy. The other is dopamine. In fact, I would claim that they're the only two things that make you happy, or anybody happy. You thought it was that purring kitten. Too cute. Serotonin and dopamine. Temperature affects how fast you can think and feel, as well as how fast you can move, and how fast you metabolize food, and how fast you do anything. This may sound trivial. In fact, few people would be surprised to learn that temperature affects his or her performance as a living organism. But after only a few minutes thought, this simple statement about temperature and performance leads us to some of the most fundamental questions of physics and philosophy. We are very quickly led to boundaries of what we can know. Terrestrial life, the life as we know it, lives in a very narrow range of temperatures compared with the tremendous range of temperatures that are available in the universe. It's just easy to see why it lives in a range. If the temperature is too cold, everything freezes, becomes a solid. And most solids don't do much. They just sit there. You know, some people would disagree and say, well, you got super fluidity and superconductivity. Yeah, okay, right. But that's a much different world than the world we inhabit. Okay, well, if the temperature is too high, well, we just turn into a gas, or maybe a plasma, where the electrons are ripped off. If we're at a temperature as high as that in the sun, we can't even stay localized. We fly off in every direction, spreading all over the sun and out into space. Well, at very high temperatures, life is no more interesting than hot air in a balloon. Life must have some parts that are solid so that life in the form of organisms can persist for long periods of time. Gases don't hang around and liquids don't hang around very much. So there has to be some solid aspects uh, to life. Um, it must have other parts that behave like a fluid, though, that can adapt to changing conditions around the organism on short timescales. So life must exist as both a solid and a fluid simultaneously. How this comes about leads to one of the most fascinating but little known stories in science. In 1827, the botanist Robert Brown noticed that very small grains inside pollen cavities experience a jittery random motion. Uh, this motion came to be called Brownian motion after Mr. Brown. The mechanism for the motion was not clear. Thoughts at the time were that it might be due to some effect of light on the particles or perhaps some hydrodynamic forces. Understanding this mechanism had to wait 80 years until Albert Einstein, in his miracle year of 1905, looked at the problem. At that time, it was not entirely clear that to physicists and chemists that matter was composed of very small atoms and molecules. Einstein was able to show that if atoms and molecules existed, then the random collisions would lead to the observed motion of the microscopic grains. This is not at all obvious. If atoms existed, then they were certainly very small, much smaller than the grains they were pushing around. A single collision of an atom with a grain would not be noticeable. Einstein showed, however, that if the grains were surrounded by millions of atoms, then occasionally enough atoms would strike the grain at the same time in the same direction as to observably move the grain. This insight was important not specifically for the understanding of the motion of pollen grains. The implications were much more far-reaching. It firmly established that matter was composed of atoms and molecules. Moreover, the world of the very small was much different than the world of the macroscopic. Small objects were constantly being knocked and tumbled. An air molecule, for instance, a single molecule in between my fingers, is being struck by other air molecules 1 billion times a second. That's a lot of violence. So this microscopic world that Einstein described is violent and chaotic. Objects are under constant bombardment at rates that would be unimaginable to macroscopic objects like us as macroscopic. Not only are molecules being knocked around, but occasionally the molecules react, leading to other molecules. A chemical reaction occurs. The more molecules present, the more often are these collisions that lead to chemical reactions. Conversely, if there are very few molecules, chemical reactions very rarely happen. Also, the greater the energy of the molecules, the more often were the reactions. Now, chemical reactions do not occur often if the molecules bombarding each other are small. For a molecule to change from one state to another requires that the molecule exists in a sea of other molecules. There's a problem, though. Our condition for life is that life must exist stably for some period of time. I mean, if it doesn't exist for some period of time, then it's not really anything. If molecules are being bombarded constantly, then how can they lead to stable life? We noted that chemical reactions occur only occasionally by microscopic standards. Uh, this is an empirical observation. We know this is true because we can measure how fast molecules react. But why is this true? If collisions that lead to chemical reactions were as common as collisions in general, then the atomic makeup of the molecules would be under constant flux. They would not be stable. So, the physicist Erwin Schrödinger pointed out in his lectures in Dublin in 1944, the reason chemical reactions are slower than the rate of collisions traces back to something called quantum mechanics, which Schrödinger had a big hand in inventing or discovering. Historically, around 1900, Max Planck, an experimental physicist, observed that light could only appear as packets of energy, not continuous. That light we think of as waves, he was seeing them as particles, packets of energy. So Mr. Einstein once again comes to the rescue. Also in 1905, his miracle year, explained this in terms of something that is known as the photoelectric effect. This is the removal of electrons from metals by shining light on the metal. Einstein was able to show that indeed light was composed of packets or quanta of energy. And in this case, when we're talking about packets or quanta of light energy, they're given the name of photons. Quantum theory describes how electrons around a nuclei or around a nucleus exist in orbitals. These are convoluted clouds of electrons. It's more subtle than that. An electron, a single electron, can be in its own cloud. Specifically in atoms, each orbital represents a different discrete energy. A discrete and specific quantum of energy is required to move an electron from a lower energy state to a higher energy state. Small amounts of energy won't do it. Here's the next energy level that the electron can achieve. An amount of energy this big must lift it up. Smaller energy won't do it. Chemical reactions require electrons to move between or completely out of their orbitals. In order to have chemical reactions, the electrons have to move this large energy jump. If the energy bombarding the atom is not sufficient to move electrons out of an orbital, then no chemistry occurs. So at biological temperatures, temperatures that we know life can exist at, the number of collisions with electrons that can move the electron out of an orbital is very small. And mostly atoms and molecules remain unchanged. So this solves our stability problem. But we have another problem, and that is we can't be completely stable or else the life can't do anything. So we can make a second requirement for life other than stability, and is that life must do something to its environment repeatedly. It's not sufficient for it to be able to do it one time, because that's not very survivable. You run across a condition, do it one time, and you can't do it again when the condition comes back. then you're not a very good living organism. In order for a molecule to do something on its environment, it must sense its surroundings and be constantly affected by it. Life must constantly interact with its surroundings in order to act on it. Collisions are the way that life samples its environment. On the other hand, collisions cannot be so great that order in life is completely disrupted. The quantization of energy states in atoms solves this problem. The energy of the bombarding molecules is great enough to move electrons between energy states that are very close in energy, but not between energy states that are very different in energy. Well, let's talk about an important specific case in biology. A very important set of forces in biology are due to what's called the hydrophilic and hydrophobic effect. These forces are much weaker than the quantum-based covalent forces that we've been talking about that hold electrons into molecules. Yet they are strong enough to cause bonding of molecules on very short time scales. So these are very weak forces that can cause molecules to come close to each other and attract or repel each other on very short time scales. Because these two types of bonds are weaker than covalent bonds, random collisions break them up much faster than covalent bonds. So really, much of the activity that we think of as activity responding to the environment occurs as a consequence of these weak effects, these hydrophilic and hydrophobic effects. And they are what allow or limit biological effects to a certain time scale, to a certain speed. Well, this brings us back to my T-shirt. Thought I'd never get back to it, huh? Well, serotonin and dopamine are neurotransmitters. They're chemicals, and the thing to note is they're in our brain, and you release some, and we get happy. Okay. All that I just described about releasing some, get happy, but all that is regulated and architected and structured by these very weak forces that I just mentioned, these hydrophilic and hydrophobic forces. And the reason it works is because the energy in the random thermal fluctuations that are going on in the molecules around other molecules is well matched to the energy in the bonds that are created by these hydrophilic and hydrophobic forces. And that is why cold beer is so very important in a steamy place like Pensacola. If I leave this air-conditioned room, go out on the porch, I better track down a very cold beer quickly. Otherwise, my body temperature may rise to a level that would just send my covalent bonds spinning, and that wouldn't be good for my health. But there's a second reason. Having the temperature at the proper level so that it's matched up with those hydrophilic and hydrophobic bonds allows me to get pleasure from the beer directly through my serotonin and dopamine. Now that is worth knowing, And we didn't even get into the uncertainty principle and quantum mechanics and all that. No, but still important. Well, that's it for today. If you'd like to meet up again in space time, hit the subscribe button below. Otherwise, from steamy Pensacola, be safe, my fellow travelers.